Hello friends, welcome to our YouTube channel all about electronics. In this video, we will be creating a 5 Good day, my name is Madeline Esendino from the Group 5 of CPE 107L Section B2, and this is my Lab 3 vlog where I will be creating a 5-bit comparator using the Microsoft Excel and Logisim. This vlog will be divided into 4 parts. For the first part, we will try to understand the behavior of comparators first, and then we will look at its truth table. From the truth table, we will construct our Kmap. And from that Kmap, we will derive the simplest Boolean expression that we can get. And then we will proceed to part 2, which is our Logisim implementation of a 1-bit comparator in preparation for the part 3, which is a 5-bit comparator implementation. And we will do that by cascading. So for part 4, we will just be summarizing everything that we have learned. Let's get started. Let us think of the word comparator. It came from the root word compare. So looking at n-bit comparator figure over here, and this slides came from our professor, Ma'am Rosemary V. Pellegrino. Looking at the inputs A and B, our n-bit comparator compares their values and provides us 3 possible outputs. It's either A is less than B, or A is equal to B, or A is greater than B. So that is why it is a multiple output component device. Let us look at the truth table of a 1-bit magnitude comparator. Looking at the red part of this table, these are the 4 possible combinations of the inputs A and B. We can see that if A and B are both turned off, then the output will be A is equal to B. And when A is turned off and B is turned on, then A is less than B. And when A is turned on and B is turned off, then A is greater than B. And if A and B are both turned on, then A is equal to B. So it's very comprehensive, right? Let us look at the Boolean expression of these 3 possible combinations. As we look at the output 1, or the A is equal to B output, this is actually the definition of an XNOR gate. So we now have a hint of what gates we will be utilizing for our Logisim implementation. But we are not asked to just create a 1-bit comparator. We are asked to create a 5-bit comparator. And we will do that by cascading. So the idea of cascading comparators is presented in this figure, where there are 2 4-bit magnitude comparators, and the output of the other comparator will serve as the input of the other comparator. So we will be assigning the most significant bit and the lowest significant bit, and the higher significant comparator and the lower significant comparators later. So this is the idea, to save time. We are saving time because we are always dependent on the input of the most significant comparator. Okay, so it doesn't compare each comparator that are cascaded. It is only dependent on the highest or order bit first. So I've created an Excel file to show all the possible combinations of cascading. So we can see here that these are the 4 possible combinations of A alongside with these inputs. So it can be A is greater than B, A is less than B, A is equal to B, or no input. So in the case where A is greater than B, or when A is less than B, then there's no problem with the output because it will just follow the most or the highest order. However, when we get an A is equal to B input, we can see that there is a variation. In the case where A is equal to B naman, in these lines, we can observe that the output is still A is equal to B. However, when we see that A is turned off and B is turned on, then although the additional input is equal to B, A is equal to B, then A is still considered as less than B because we are following the most significant bit. And our most significant bit is A in our case. So the same way goes for when A is turned on and B is turned off. And this pattern is also the same when there is no additional input. Okay, let us now move on to our Kmap. So I've already prepared 3 Kmaps for the 3 outputs that we can get. Let us first look at when A is greater than B. So when A is greater than B, this is column F. There are 4 instances where the signal will be turned on. And those instances are these light pink shaded over here. So looking at this Kmap, we can classify 2 groups. The first group will be this and this. The second group will be this. But what are those X's for? These are the don't care outputs. But why is it considered a don't care output? Because if we look at the additional input, both high and low, I'm sorry, I forgot to mention that H stands for high when A is greater than B, E stands for equal, and L stands for low when A is less than B. So if we think of it logically, a number can't be both greater than or equal to itself. So therefore, these are highly unlikely outputs. So therefore, they are considered as don't care outputs. Moving on to our Boolean expression, our first group will be these 2. So we can see that for these 2, lagyan na nga natin ng box. For these 2, and they are considered as one group. Okay? For this group, A and B are both constants. A is constant and B is also constant. However, it is in its complement form because B is 0. How about for the vertical comparison? We can see that the equal input change, so that is cancelled, while the high and the low signals stay in their complement form, H and L, because they are both 0 here. Moving on to our next group. What is our next group? This is our next group. We will maximize this so that we can come up with the simplest min term. Okay, that's our second group. We can see that we can already cancel A and B because they are inconsistent. However, for the horizontal comparison, we can see that E is also cancelled, 0, 0, 1, 1. H is consistent, 1, 1 in all 4 possible combinations. And the low signal is also cancelled because it's 1, 0, 0, 1. It is inconsistent. So the final min term will simply be H, or the high signal. Moving on to our next output. What is our next output? Okay. We have A is equal to B. And for A is equal to B, we have how many, it's the column G, how many signals where it is turned on. We have 4. And those 4 outputs are the ones shaded light pink here. So we can see the first group is this group, these two. We can form 2 groups for our Boolean expression, and our first group is these 2. We can see that A and B are constants in their complement form. For the vertical comparison, we can see that E is cancelled because it changed from 0 to 1. However, the high and the low signals stay in their complement form. How about our second group? Our second group are these 2. We can see that A and B are also constants. They are both 1 here, so we'll just write AB. However, for the vertical comparison, it is the same as the first group, where E is cancelled and H and L stayed as their complements. However, we can still simplify this. We can factor out HL because it is common to our minterms. So let's factor them out. So momentarily, our Boolean expression will look like this. However, if we examine what's inside this parenthesis, we can see that this is an XNOR function. So let's write that out. HL A XNOR B. Okay. For our third output, how many groups can we form? We can also form 2 groups. This is the first group. Our next function is A is less than B, and it is column H. And there are 6 possible outcomes that turns into 1, and those are the light pink shaded here. So our first group are these 2. We can see that A and B are constants. So let's write them out. A is in its complement form and B is as is. Then we can see that E is also cancelled because it turned from 0 to 1. However, H and L stayed in their complement form. What is our next group? Our next group is this group. And we can already see that we may cancel A and B because they are inconsistent. However, for the vertical comparison, we can see that E is a constant in its complement form. H is cancelled because it changed from 0 to 1. L will stay. So this is the final form. Is it the final form? Yep. We can simplify this further. These 3 are the final Boolean expression that we have for our comparator. Moving on to the part 2 of our vlog, I've already prepared a Logisim circuit file wherein the AND IC, the OR IC, the XNOR IC, and the inverter is already present because these ICs are what we are going to use to implement the 3 Boolean expressions that we derived from our Kmap from part 1. So now we will add a circuit and name it our 1-bit comparator. Yan, so sobrang dull niya na kasi pagka hindi ko fast forward. So explain ko na lang yung ginagawa ko sa video. Sa left side, naglagay ako ng 3 inputs which will serve as the equal, the high, and the low signal. Tapos naman sa right side, meron tayong nilagay na 2 pang input ulit which will serve as the signals A and B. Tapos sa gitna, nilagyan ko ng inverter para madali lang hugutin yung mga input signals na kailangan. Tapos yan, nilalagyan ko lang sila ng respective labels. Tapos nalilito ko dun sa facing. Yan. Tapos nilagay ko sa sticky notes yung mga Boolean Expression. Tapos sinignan ko yung unang min term para sa equal output yon. And then, yan, kinonect ko na. Kasi sabi, inverted high signal tsaka low. Naka-AND to each other. So, naglagay ako ng AND IC. Tapos, nilagyan ko dyan ng XNOR kasi kailangan natin XNOR yung input signals A and B. Tapos, yung dalawang yon nakita ko na naka-AND sila together. Tapos, yun na yung ginagawa ko dyan. Yan, pinakita ko lang na tapos na siya. Yan, tapos linash ko lang, lalang. Tapos yung next min term na, which is the high output. So I'm creating the necessary combinations. Nagdagdag ako, kinulang ako ng AND IC. Tapos nakita ko na naka-OR siya sa H. So naglagay din ako ng OR IC. Tapos nalilito na ako dun sa wiring kaya nilagyan ko na ng output signal agad. As you can see, naka-on na siya. So that is a hint that we are doing the correct process because, joke lang, hindi pala correct yun. Nagkamali ako ng wiring dun. Yung naka-1 dyan, yun yung equal output. Kasi lahat sila naka-0, so makes sense. Ayan, yung second one daw, slinash ko na ulit, ay yung signal na katabi ng equal na yan. So, for the final min term na tong, ginagawa kong connections ngayon. Tapos nalilito-lito na ako kung saan ko lalagay yung wires kasi di ko naman talaga plinano yung paglalagyan nila. Yan. Trouble. Nag-iisip na ako niyan. Ano kayong gagawin? Okay. So, nagawa naman ng paraan. Pinalabas ko na lang doon. Kaso lang, sa totoong buhay, marami tayong wire na magagamit. So, wag niyang tularan. Planuhin. Tapos, ayun, may butal na isang AND IC. So, yun, di talaga naiwasan gumamit tayo ng 6 na IC para dito sa ating 1-bit comparator. And that's the final output, which is the low signal. Now that we've already created our 1-bit comparator using Logisim, let us now check if it works as intended by comparing the input combinations along with its output using our Excel file. So in the case where the output is greater than, or when A is greater than B, the input combination wherein a high signal is present, that will trigger this output, regardless of the combination of A and B. So let's check using the poke function. So we place the high signal. Now if we try to change it by doing some combinations for A and B, it is unaffected. So that's correct. How about for the other two scenarios? If A is turned on, B is turned off, and equal sign is turned, and an equal signal is turned on. If A is turned on, B is turned off, and an equal signal is turned on or off. So it still outputs a greater than sign. So that's correct. How about in the case where A is equal to B, we have 4 turned on signals. In the case where A and B are both turned off and the equal sign is turned on, and when A and B as well as the equal signal is turned on. Let's check that out. Equal, A and B are both turned off, it's turned on here. A and B are both turned on, and it's turned on here. How about in the case where no input signal is present? So it is still an equal output. Both are turned off, it is still an equal output. So that's correct. How about in the case where A is less than B? So if there is a low signal, automatically, regardless of A and B's combinations here, it is always a low signal. Let's check. There's a low signal here. It is always low regardless of A and B inputs. And that's correct. How about for this case? When A is turned off, B is turned on, and then equal signal is also turned on. A is turned off, B is turned on, and an equal signal is there. So it is unaffected, as well as no input. So it is still less than. So we now verified that this 1-bit comparator is accurate and fully functional, and therefore cascadable. Moving on to the third part of our vlog, wherein we will be creating a 5-bit comparator na talaga by cascading this 1-bit comparator that we have created in our main circuit. So how are we going to do that? We just simply drag it and place a label. Pangalanan na lang natin siyang 1-bit. Once again, fast forward ko yung video dahil parang mali-mali yung sinasabi ko dun sa original video, tapos nabubulol-bulol pa. Also, nag-trial and error ko ano yung pinakamagandang formation, but then I decided na pababa na lang sila, just like my mental health. And so, the output of the preceding comparator should be the input of the next one. And then I'm placing a 5-bit input sa taas, which will serve as the A input signal, and another one sa baba, which is the B input signal. And then I'm just adjusting things and adding a splitter so that I can distribute their signals to the 5 comparators that we have cascaded. So I'm just connecting them respectively. Nalilito-lito pa. And kinakabahan kasi baka mag-error. Bakit naka-red yung gitna? Dahil wala pang ground. Marirealize ko yan sa may gitna. So I'm just finishing the inputs for B. And finally, nag-decide na lagyan ng null input or ground. Kasi na, yung final outputs natin. Equal, high, and low. So this is now the final form of our 5-bit comparator using Logisim. We have cascaded 5 1-bit comparators together, and we got this output. As you can see, the output of the first or the most significant comparator is connected to the next or the lower order comparators. So that means that whatever is the outcome of um, of the most significant bit, it will be unaffected by the lower ones. As you can see, it is still a high signal even though I turned all of this on. If they are equal, then the equal output is turned on. If it is a um, less than output, then it will always be less than, regardless of what I do with the other comparators here. So it just follows the output, the final output just follows the most significant bit here. So that concludes the part 3 of our Lab 3 vlog. So as a review, we have learned that comparators are components, electrical components, which compares two values, A and B, and produces three possible outcomes, which is the equal, the high, and the low signal. And then for us to be able to create a 5-bit comparator, we simply cascaded the 1-bit comparator that we have created. And so we can produce this type of circuit wherein the output signal, the final output signal of the 5-bit comparator is dependent on the most significant bit. That concludes my Lab 3 vlog. Thank you for watching!